All right, so when they got the third harmonic frequency with 3 nodes, you had a fixed end, and you had one. Now, technically, the end that Alice or Jane was moving up and down, it was technically a node, but it was moving a little bit because they were oscillating. But on a wave on a string, this is considered a node. This is a node. This is a node. So on the third harmonic frequency, you had 3 nodes. If you went to 4, you would have 4 nodes, etc. Okay. So we're going to do the same thing, except we're going to do sound waves in a tube. So if you take a tube and you send some sound waves down, now in reality that looks like a bunch of little particles that are all packed together. So that's what the sound wave actually looks like. I'm going to model it with a transverse wave, which is our classic type of wave. You can get the same standing wave, so this is called a standing wave on a string. You can get a standing wave in a tube for sound. Now the way that that ends up looking is for a standing sound wave in a tube, you're going to have a node at the end of the tube. So the sound wave is going to go down, it's going to hit the end of the tube, and it's going to come back. And for a sound wave in a tube, we always have a node or a place where the amplitude is 0 at the end of the tube. So this would be your first harmonic frequency. And so before we had like Fn equals 2. I don't want to get this wrong. I want to make sure I get it right. If anyone has it in their notes, they can let me know what it is. But we did do this last time. Transverse wave.
Vn over 2L.
Perfect. So we had Fn for wave on a string. So this was up here. Fn equals Vn over 2L. So n is the number of nodes. For this one up here, n would be 3. V is the velocity of the wave. L is the length of the string.
To find Fn.
And that,
What does that mean?
Fn, this would be the frequency of the, in this case, the third harmonic frequency. So it just depends on how many nodes you have. You could have F1 if you have 1 node, F2 if you have 2 nodes. This would be F3 in this case.
L is length and V is what?
L is length of the string, V is the velocity of the wave.
And N is how many nodes?
Correct.
Length of the entire.
Right, the entire string. So L would be like here to here in a straight line. All right, so we have a similar equation, except for wave on a string, the first, so if you do it with only 1 node for wave on a string, it looks like this. This was when, I think we watched a video of a guy where they were holding the end and they just went up and down and there was just one big oscillation in the middle, like this. And we talked about how many wavelengths this is. How many full wavelengths is this? This is half of a wavelength. So it's half because you go up and down, but you have to complete the wavelength, you'd have to go down and back up. So that is half a wavelength. How much of a wavelength is this?
4.
This is a fourth. So you go from the midpoint to the top, and then to complete your wavelength, you'd have to go from the top back to the midpoint, midpoint to the bottom, bottom to the midpoint. So it's only 1/4 of a full wavelength.
Or a
Yep, so the time for this would be 1/4 of a period. Yep. So the time is period, the length is wavelength, and this is 1/4 of wavelength. Which means for this one, so this equation was for wave on a string. So for resonance or standing waves, standing sound waves, and standing wave just means a wave that's keeping on doing the same thing. So if you maintain that frequency, the wave's going to keep going up and down in the same spot. Same thing with sound waves. You can get it to have this resonant frequency, it's going to maintain that if you keep going at the same frequency. So standing wave, this equation Fn equals Vn over 4L. Now we have 4L because as was pointed out, this is a fourth of a wavelength, not a half of a wavelength. So we start at half a wavelength for standing wave on a string. We start at a fourth of a wavelength for standing wave, sound wave in a tube. So the equation is slightly different. This is sound in a tube. Oops, sound in a tube. Okay, the other thing, Andrew, can we turn off the screen, please?
See, if you're undergoing an oscillation, you have to jump over each axis. It is kind of a wave pattern.
That's really. Okay, we also did. Yeah, if you look, you'll find all kinds of ways to plot, like little dinosaurs jumping. Okay, wavelength, and we had before that it was. 2L over N. This just goes to show you, I can pull kinematics equations up out of my brain anytime. Wave equations, waves are not my strong suit. That's okay. We can do it anyways. So we had this, again, this was for wave on a string. So for wave on a string, this was our equation to find the wavelength. So 2L over N. What do we think our wavelength equation will be for wave in a tube? 4L over N. Nice.
Actually, I already said that.
You copied me actually first.
Alice got there first.
Yep.
Okay.
I think the sound waves are just coming a little slower for you, Mr. Byron.
Must be the temperature of the air.
That's what I'm saying.
So why is it 4?
It's 4 because we said that if you start with the what's called the resonant or like base frequency, the first mode that you can get is where you just have the thing moving in the middle and two ends fixed. Then you can go to 2, then you can go to 3. But the first one is half a wavelength. So to get a wavelength for x equals 1, or n equals 1, if n is 1, which is this case, the wavelength of this wave is 2L divided by 1 because we have to go twice that distance to get a full wavelength. In this case, the wavelength for n equals 1, if n is 1, is 4L because we have to go 4 times this distance to get one full wavelength. And then the frequency equations are just related to that as well. Vn over 4L versus Vn over 2L. Now, the one other thing for resonance that we need to hit on is we can have resonance in a tube that is closed at both ends, which is pretty cool. But when that happens, we have a node at both ends, and there's a specific rule that goes with waves, resonant or standing waves in a closed tube, and that is we can't have a wave that goes like this. Because this is, how much of a wavelength is this? 1/2. So this is half a wavelength, and you can't have a wave that's going back and forth in a tube with closed ends, a sound wave, but you can't have that happen if it's only half a wavelength. This can happen because it goes out of the open end and it just keeps going. So that's fine. Our wave can still have full wavelengths and it can go on forever and ever and however long it wants to. Inside of a closed tube, we can't have this. Instead, because we have to have at least one full wavelength to have the wave traveling within the tube. So we'd have to have this, the starting one here would be this. So that is your like base for a tube that is closed on both ends. So the base n, or the base number of n nodes for a closed tube is 3. So you have to start with your 3. Now, you can go up from there. However, we can't have 4. Because if I try to do 4, try to do that quick. If I try to do 4 nodes, 1, 2, 3, 4, I'm going to start here. I'll go up, then down, then up, then down. I have 1.5 wavelengths. Again, I've got a half a wavelength. I can't have that. I have to have full wavelengths. So when a wave is going back and forth in a tube, we're not allowed to have half wavelengths within that. They've got to be full wavelengths, which means that N for standing sound waves in a closed tube has anyone picked up what the mathematical thing for N will be? Yeah, so there's a thing about it. It will always be something. Odd, yes. So Liam noticed that if we can't have 2, because if we have 2 nodes, it's half a wavelength, so that doesn't work. We can have 3, because that's 1 full wavelength. We can't have 4, because that's 1.5 wavelengths. But we can have 5, because that would be 2 full wavelengths. So we can't do 2, we can do 3, we can't do 4, we can do 5. So the N for standing sound waves in a closed tube is always odd. Always odd. So open-ended ones, we can have whatever. We can have however many nodes within this. But for a closed tube, we have to have odd number of nodes or an odd end. Other than that, so these equations, you've got for a string, you've got lambda n equals 2l over n, fn equals vn over 2l, and for waves sound waves in a tube, you've got the same thing except you have 4l instead of 2l.
Can we write these down?
Yeah. Yeah, I mean I think they're not on the AP equation sheet, so on the AP test, you would have to know them, I think. You have to have them memorized if you are taking the test. Or, yeah, memorized or however you want to know them.
Lambda n are the same for both tubes? Like the equation?
The general equation, yes. Yep, so it doesn't matter whether you're, the only thing is like you'll never have, this will never be 2 for a closed tube. It'll just be 3 or 5 or 7.
And it'll always be long for node?
It can be any amount. So let's say, I'll do a different one on this one just to show us. So let's say we want to do, let's say a wave that starts here, it goes down, up, and down, and up. So I've got, oops, I think I made that, I think I wanted to go this way. There we go. So you've got a node here, node there. So this would be n equals 3. So yeah, you could have a wave in an open tube that was 3 or however many. So n for standing waves in a closed tube is the only one that has that restriction that it has to be odd because we have to have full wavelengths. We can't just have a half a wavelength or the wave's it's not gonna work out, because if we have half a wavelength, we wouldn't have a standing wave because it would hit here and then it would go down and then it would go up and we'd start having destructive interference and it wouldn't be a standing wave. So a standing wave has to have full wavelengths in a closed tube. All right, the last thing will be the Doppler effect.